Okay, in this video I'm going to talk about the connection, sort of walk you through the steps from the idea of a Riemann sum to the Riemann sum, right? That's what we get when we add up all those rectangles, right? We got rectangle plus rectangle plus rectangle, and we use that to approximate the area underneath the curve. I'm going to walk you through how we go from there to the definite integral. The definite integral is the precise value of that area between the curve and the x-axis between, over some interval from a to b. So I'm going to walk you through how we go from the approximation to the definite integral. And this is in the process we're going to really define this thing, the definite integral. So let's try this. All right. So suppose we've got a graph, right? And we've got a curve, right? Let's say that looks like this. Okay, and we're going from, let's say, A here and B here. Now the idea in the Riemann sum is that we take this space between the curve and the x-axis, between A and B, and we divide it up into rectangles. Alright, so it's going to look like, we're going to have one rectangle, and we'll have another rectangle, and we can do different numbers of rectangles. For this purposes, we're going to assume that each rectangle has the same width. Okay, obviously it doesn't look like they do, but let's just pretend. So we're going to assume they all have the same width. Now we talked about Riemann sums. There's a couple of different ways to do them. One is called a left-hand Riemann sum, is that you take the value on the left-hand side of your interval, and that gives you the height of your rectangle. So that would look something like this, and like this, and so on across there. And the other way to do it would be to make a right-hand Riemann sum, which would be to say you make the height of the rectangle based on the height of the function on the right side of your interval, so something like that. Now, one thing you want to notice, two things actually, is that the smaller we make these rectangles, or the more rectangles we have, well, the more rectangles we have, the smaller the rectangles, the narrower each rectangle is going to be. And the more accurate our approximation is going to be, because there's going to be less like little extra space that's either below or above the curve. So more rectangles equals more accurate. The other thing is, the more narrower we make this rectangle, and you can imagine if we zoomed in on this rectangle really, really close, or zoomed in on the curve, so let's imagine it looked like this. If we zoomed in on the curve, and we imagine that our rectangle goes from here to here, let's say like this, well, the closer we get together, the difference between the height on the left-hand side and the height on the right-hand side becomes very negligible, right? It becomes very, very small. So it doesn't really matter whether we're doing a left-hand sum or we're doing a right-hand sum. Okay, so more rectangles means more accurate. It also means that the difference between the left-hand sum and the right-hand sum is not going to be very big. So what we're going to do, instead of deciding to use a left-hand sum or a right-hand sum, we're just going to use some random value, x value, on the interval. So we'll call this Ci. So Ci is a random x value on the ith interval. Right? So we're taking our rectangle, and we're just picking a random point in here, and we're using that to be our height. Okay, so what does that look like? Well, we're going to have a rectangle. Look over here. All right, I've got a rectangle. Okay, it's going to go from some x value to some other x value, so it's going to go from here to here, right? And we're picking some point in here, C, that's going to be, it's going to determine the x value, the height, and so their height's right here. So the height will be f of Ci, and the width of this rectangle is just delta. We're going to call that just delta x, and the delta x is going to be the same for each rectangle, right? Because we're doing some number of we're going to do some number of rectangles, and each rectangle is going to have the same width. So the area of this rectangle, which is just what's called the ith rectangle, if there's however many rectangles, is just going to be f of c sub I times delta x. Okay, so that's our basic idea. Right, we've got one rectangle, area is the height, which is the height at that x value, times delta x, which is the width, and the width is the same for each rectangle. So we could say if I was going to take all the rectangles and add them together, so that would give me the total area. So the total area of my Riemann sum with equal subintervals, is going to be the sum from I equals 1 to n, where n is the number of rectangles, of f of sub ci, or f of c sub I times delta x. So there's my total area. Now, one thing we know is that the more that we increase the number of rectangles, the more accurate this is going to be. And if we want to get it more and more accurate, we want to think about what's happening as this n goes towards infinity. Well, now we're talking about limits. So what do we have? Let's look over here. So if we think of a precise value of that area under the curve, well, let's go back here. All right, we're making the infinite number of these rectangles. The area, the total area, is going to be the limit as n goes to infinity of that sum that I just talked about, from I equals 1 to n of f of c sub I times delta x. So this is not going to be just an approximation. This is actually going to be precisely the area underneath the curve. As n gets closer, the limit as n goes to infinity of this whole thing, of this sum of all these areas. And we define that as the definite integral from a to b of f of x dx. So that's where we get this idea of a precise definite integral. Now, I talked in another video about like what this means in the fundamental theorem of calculus, but this is where we're defining how we're defining this definite integral.